Okay, so up next we have Pablo Brewer, who is the director at the Center for Information Warfare and Innovation. All right, thanks. Give him some applause.
Hey, thanks. Thanks for coming out. So I'm going to talk to you a little bit about snake oil and how we're going to live with snake oil and the fact that it may be okay as long as you realize that you're buying a little snake oil. So mandatory disclaimer, these views are my own. They're not that of my employer. Not mandatory disclaimer, vendors are fine people. So if you're a vendor, please don't await me with pitchforks and torches after I'm done with this talk. They're InfoSec professionals just like the rest of us. They got to make a They do the best they can developing products, but they at the end of the day they also need to make a buck. So last time I gave this talk at Circle CityCon, a friend of mine that happened to be a foreigner came up to me and went, "Hey, great talk, but what does snake oil actually mean?" So for the foreigners in the room, let me define snake oil. Snake oil is an American colloquialism, and it's based in the days of the Wild West when they would sell these fraudulent tonics that may or may not include snake extract that had very, very little, if any, benefit whatsoever. And carried it on and now refers to any product with questionable or unverifiable content or benefit. So that's what I mean when I talk about snake oil. So, brief scoping here, brief explanation of in history of exploitation. And what I've got the defensive measures in black and the quote-unquote offensive measures in red. In 1971, we've got the creeper virus. Two guys in Pakistan, literally in a mud hut, developed this thing just because they could, not with any malicious intent, but just they wanted to develop some self-propagating code. And then 1986, Dr. Dorothy Denning comes up with the idea of IDS. And then 86, we get the brain virus. And 87, John McAfee, before he decided to become a South American warlord, develops this antivirus thing. And then, 1991, Los Alamos actually goes through and develops an IDS, and Check Point comes out with the first stateful packet inspection firewall. And then 1996, we get Smashing the Stack for Fund-and-Profit. It is not the first time that this topic was written about, but it's the one that most people know. You can still go out there and read Alepht's paper. Just remember it's an AT&T syntax, which is just maddening to me, but there you have it. And then here's kind of an interesting thing. 1997, the Return to libc paper is written. And it gets largely ignored. And it gets largely ignored because the old Smashing the Stack thing still worked. And so it gets, just remember that gets written in 1997. Then, 2003, IDS finally becomes commonplace, right? So it was suggested in 1986, developed in 1991, 2003, finally most companies have this thing. And then 2003, Metasploit gets released publicly and people lose their minds. I think my favorite quote about Metasploit when it came out was, "This is like the ice cream man handing out dynamite to kids." I still use that one. And then 2005, Intel develops the XD bit, which is to prevent what Aleph 1 talked about in the Smashing the Stack for Fun and Profit, but it's only the Intanium servers, right? So these are, this is about as close you get to a mainframe without actually being mainframe. So you only find it in big, expensive businesses. 2006, rise of 64-bit architecture means that we finally have stack smashing protection via the non-executable stack, that execution prevention, and address space layout randomization, which is great. So in 2006, we finally mitigate the stack smashing stuff, and now all of a sudden, right, the offensive folks go, "Hey, that return to libc, that guy was onto something." Right? And so by the time we develop DEP and ASLR, we already have a technique for bypassing it. Shortly thereafter, the next year, we get return-oriented programming, which is really just an extension to the return to libc attack. And so what we get is this nice ping-pong back and forth between the offense and the defense. So the good news is you're all going to be well employed. That's the good news. The bad news is we're going to keep buying products that aren't really going to protect us in the way that we would like them to protect us. So just kind of keep that in mind as we go through this presentation. So why are we here? Most people that work in InfoSec are not computer scientists. Just straw poll. How many of you have a computer science degree? There's a couple of you. Okay, if you had to suffer through automata and you don't know why, you'll learn why. Don't kill me because I'm going to teach all these folks the salient points of automata in about 35 minutes. Okay? So, why does it matter that most InfoSec pros aren't computer scientists? Well, computer scientists have to suffer through this class called automata. I say suffer because every major kind of has a weeding out class, and for computer scientists, it's automata. It's a very, math and notation intensive course about computational theory and complexity. And that computational theory allows us to very quickly figure out if something is snake oil or not. If you'll pardon the language, it is the ultimate bullshit flag. And you get to throw it a lot when you're talking to vendors. And so recognizing that snake oil and being applied that computational theory allows you to, kind of avoid this conversation, right? So the boss comes in and goes, we can't do the breach thing. It's too expensive, we're losing too much, you got to make it stop, right? And then what happens is, Joe Vendor shows up and says, you need our next generation box full of Pew Pew Magic proprietary technology. And it's full of ODA detection, and it's going to cure all of your woes. And then people that aren't computer scientists, allow themselves to, hope briefly. And when we go, really, you can detect ODAs? And then we get told, yes, DNC, your email will be totally secure. I made these slides up before that whole thing broke. It was just a happy coincidence, I promise. And then they go off and they tell us about their patented Pew Pew and magic sauce and snake oil, and you get those conversations and you're not really sure how the product works. And we'll talk about some of that language. And then we throw a bunch of money at them, right? And the vendor does this with our money. And then 90 to 180 days later, an APT comes along and there's our network, where APT is defined by anybody that could bypass your magic box full of Pew Pew technology. Right? It very well may be a 12-year-old with a dial-up modem and an AOL account, but they got past your next generation defense, so clearly they're an APT. So who's been to a vendor page recently and read a product description? Right? Let me know if you haven't seen one of these terms. Holy crap, what does any of that mean? State-of-the-art, adaptive defense, next-generation, threat analytic, multi-layer hunt, end-to-end, cyber anything, really. I feel dirty just saying the word cyber. Virtualized, cloud-enabled, threat-centric, digital DNA, big data, software-enabled, and I'm going to pick on Sans here. What the hell is a forensicator? I just want to know. There's the machine learning one, but we're going to get, but this, the first time I gave this talk, I gave a very short version of this talk that unfortunately didn't go well at B-Side San Francisco, and it happened to be the same time as RSA. And so I went to the RSA vendor area, and I couldn't have planned it better. I saw what in the wow world? First of all, the marketing people didn't think this out through very well, right? Because I don't know that I can say COIP in polite company. It just sounds dirty, right? Second of all, cloud, somebody else's computer. Unless you're running Novell NetWare, it's probably going to be over IP. So it just seems a little redundant to me. Anybody here running NetWare or IPX, SPX? I'm just curious. No? All right. You still got, don't laugh, I still have WWIV source code in C on a floppy disk. I still got it, I'm that old. So, when I see cloud over IP, the first thing I think is, cloud is made of servers, and then I look at the vendor kind of like that, right? Because I don't even have words for that kind of language. So how do we get past the marketing speak? Well, we're going to computer science the hell out of it, right? We're going to talk about a little computational theory. So there's this guy, you may have heard of him. His name was Alan Turing, right? And he developed this thing called a Turing machine, which is an abstract machine, a mathematical model, used to prove fundamental limitations on mechanical computing, okay? And something is said to be Turing complete if it's theoretically capable of expressing all tasks accomplished by a computer. This is any computer. I don't care if it's an IBM mainframe. I don't care if it's your iWatch, your iPhone, your Android, your PC, your Mac. This is all computers. And automata is this field of discrete math that studies computers and the problems that can and more importantly cannot be solved by computers. Okay. So very roughly speaking, automata breaks up problems into three categories. There are solvable problems. These are considered easy. They can be solved in what's known as polynomial time. There are intractable problems which are hard, and there are undecidable problems which are impossible. And it doesn't matter how fast your computer is, it doesn't matter how much RAM, how much hard drive, you can reuse the entire AWS resource pool and you are not going to solve this problem. So I'm not going to talk about the easy problems. We're going to talk about a hard problem and an impossible problem. And then I'm going to show you how those are enough for you to tell that you're buying snake oil from vendors. So one does not simply solve an NP hard problem. Okay? So what is an NP hard problem? I'm going to describe one to you. The most famous one is known as the traveling salesman problem. And traveling salesman, or TSP as it's known, is explained this way. Given a list of cities and distances, what is the shortest possible route where the salesman visits each city and returns back to the original city? Seems fairly simple, right? Not that hard. Remember that there's only one optimal path. There is only one correct answer. And that answer is the most efficient. It's not sufficient to be efficient. You have to be the one most efficient answer. And it turns out that this problem is really hard for computers. And the reason it's hard is this. Let's pretend that we have a traveling salesman. You just have 5 cities, right? You have 5 cities. So when you start out, how many cities do you have to choose from? You have 5 cities, right? You can start at any of the 5 cities. All right, I'm going to pick my starting point. I have 5 cities. And then how many do we have left to choose from? We have 4. And then we got 3, and then 2, and then 1. What mathematical function does that look like? It looks like a factorial, right? So it turns out that the running time is factorial. So that is non-polynomial time, right? Number of cities is n, and the running time is a factorial of the sample size that I have. So the running time for this thing seems relatively simple, but it's a factorial time. So let's think about this. If you have to generate the most efficient path to go from New York to San Francisco, there are 19,354 cities in the United States, and you have to try every possible combination in order to get the optimal answer. If you do that factorial, and you do one calculation per millisecond, it takes you 110 centuries to solve. Right? Almost 111 millennia. Who wants to hang out for that? Anybody? No? There's always one, right? So a deceptively simple problem. It's certainly easy for me to describe, but there are a lot of calculations involved. So, why do I care about TSP? Well, you care about TSP because TSP is analogous to a lot of problems that we want to solve in computation. Optimal routing, right? I want my packets to get from point A to point B in the most optimal path. Well, that's a TSP problem. Detection of man-in-the-middle or race conditions. That's a TSP problem. Resource use optimization. Search algorithms. Crypto problems. Basically anything where you want optimization is going to be reduced to a TSP problem. Yes, sir? If you don't know the optimal routing, how do you know that you don't have a man-in-the-middle attack? Yeah? Okay, so if solving traveling salesman problem is hard, then solving all of these problems is also hard to do via computation. So right at this point, somebody goes, hey, look, I drove here from wherever, and I used a GPS, and it got me here, and it definitely did not take 110 millennia. So let's examine how that happens, right? So GPS works because it makes a bunch of assumptions on your behalf. And so some of those assumptions make sense, right? You're not going to start, your starting point is going to be right where you are. It's not going to be any of those 19,000 cities. Your starting point is where you are, and it's going to make assumptions that interstates are faster than rural routes, and rural routes are faster than farm roads. And then you're going to tell, don't show me toll roads, and don't show me ferries, and it's going to assume things like loops are bad. And so those assumptions drastically reduce your calculation space. They drastically reduce the sample space, and so you get a workable solution. Notice I said workable. It's not optimal. Well, in the security space, if it's not the most optimized solution, you're going to have type 1 and type 2 errors. That means you're going to have false positives and you're going to have false negatives, right? So who's ever, followed their GPS and they end up with something like this, right? Where it goes, Yeah, turn left here and you're looking at a building, right? So that's when those assumptions fail. And it's okay most of the time because most of us aren't playing Pokemon Go where we're following GPS directions and we can actually look left and see the building, right? So we don't actually turn into it. So traveling salesman is hard, but you can solve it if you make some assumptions, right? Those assumptions have to be good assumptions. But how does that saying go about assumptions? Yeah, I'm not going to say that because I'm being recorded, but yeah, something like that. So if the vendor tells you that they're solving a hard problem, they're making assumptions. You probably need to figure out what those assumptions are. So ask the vendor. So that's a hard problem. Who wants to see an impossible problem? It turns out that the impossible problem is actually easier to explain in theory. Now remember, when I say impossible problem, this means that no computer ever following the Turing model will be able to solve this. Period. It's not a Moore's law or House's law problem. It's not a resource problem. It's not a quantum computing problem. Until we do something fundamentally different than what Turing suggested, we're not going to solve it. So here it is. Given M, a machine M, an arbitrary Turing machine with an input alphabet sigma, let omega be an element of all possible strings. Will M halt on input string omega? Who remembers this from Automata? Awesome. The rest of you are looking at me like this. All right, let me draw you a picture. I'm going to draw you a picture. Here it is. So there's your picture. There's your Turing machine M and your input omega. You're going to compute, and then you've got a decider state. So given the reduction state, if the Turing machine state is decidable, then this is a decidable problem. Oh. No standing ovation. All right. KISS principle. Keep it simple, stupid. Here we go. Given a computer program and input, you will not be able to determine, via computing methods alone, whether it will ever finish running. So I give you a program, I give you an input to the program, you feed it to some analysis computing machine. It's never going to be able to definitively tell you if the program will finish running with that input. Why is that? Well, let's consider the options, right? So you've got this big analysis computing machine running on, the AWS cloud there somewhere, and you feed it the computer program, you feed it the input, and it finishes. Woohoo, success. But what if it doesn't finish? Well, it might be stuck in an infinite loop. It might be running properly, and it just needs more computing time, and you never really know if it needs more computing time. So you wait an hour and you pull it, maybe it needed an hour and 10 minutes. You wait a week, maybe it needed a week and 1 day. So you never really know, or possibly you just haven't accepted the upgrade to Windows 10. I'm not sure, but either way, you don't know why it didn't finish running. You just know that it hasn't finished running, right? So this is basically a logic problem. There's no way to get around this, and it's not a computing issue. I'm always going to be able to develop some program and some input that's going to run a little bit longer than you're willing to wait. Okay. So certain problems are provably undecidable, therefore impossible by computing. And so they're going to require substantial assumptions be made. Same thing for hard problems. And so vendors are going to come to you, and they're going to tell you that they solved one of these hard or impossible problems. So can anybody tell me what the halting problem is analogous to? Yeah, antivirus. This code is definitely bad. It's definitely malware. Well, if you've got a signature, then sure, it's malware. But if you don't, then I don't know. I can't tell if it's going to halt, let alone if it's bad. So when they claim they solved a difficult problem, right, hard or impossible, let's assume that they have. I'll give you the benefit of the doubt, right? You're all fine individuals. You're InfoSec professionals like I am. And then I'm going to imagine that I can take that vendor solution and I can package it in a chip. Okay? And then I'm going to use that chip to see if I can solve an undecidable problem. And if I can use your proposed solution to solve an undecidable problem, then I'll have a proof guy contradiction because I know I can't solve an unsolvable problem. And if your algorithm solves an unsolvable problem, you also didn't solve your problem. Right? So the vendor says, we detect O days. Now, let's be fair to the vendors. I've not heard, actually that's not true. I've heard one vendor actually tell me our new product, our new next generation product solves all O days, finds all O days. Normally, vendors are a little bit smarter than that. They leave themselves out and they say, we detect O-days. We want to hear we detect all O-days, but they rarely say that. So let's assume that's true. Let's assume they've got this O-day detector with this magic inside. And then we're going to put that magic O-day detector inside of the halting machine. And I'm going to define all halting states as safe code and all non-halting states as malware. Cool, I solved the halting problem. But I can't. I can't solve the halting problem. And if I can't solve the halting problem, then you can't give me an O-day detector. That's just not how it works. So that's what's called a proof by contradiction. Except that, right, earlier this year, right, April 19th, MIT releases this thing saying, MIT builds an artificial intelligence system that can detect 85% of attacks. MIT's got some smart folks. Who believes that? Anybody here believe that? All right, so I got forwarded this like by 600 people. Maybe not quite that many, but I'd given this talk before and I got forwarded this. Hey, look, the MIT guys, they figured stuff out. They're smarter than you are. And I went, okay, yeah, they're smart. I didn't go to MIT. I went to a different school, but let's read the fine print. So I went to the MIT, I went to the MIT homepage because I thought surely the mission is accomplished and I'm out of a job now. And I read their assumptions, and it says it presents its findings to a human analyst, and the human then identifies which events are actually real events and which ones aren't. So I'm just imagining like this big box with blinky lights, and there's like a midget inside of it that like takes a slip of paper and goes, no, this one's real and this one's not. So really, you two MIT, come on. I just can't. But never mind the details, right? Let's just go with that 85% thing. 85% is pretty good. That's a solid B. So let's say 1/100th of 1% of people on the planet can write you one O-day a year. Seems like a reasonable number. 1/100th of 1%, one O-day a year. So let's look at China, who has 1.35, almost 1.36 billion people. 1/100th of 1% write you an O-day, 85% of them are detected, right? So they write 13,500 O-days a year. We detect 85%, that's 11,000. That leaves 2,036 unidentified and unmitigated O-days a year. And that assumes that we block 100% of known attacks, that those humans that get that input make instant decisions, and they're always right, because humans are infallible. That's why we have computers. So 85% is really not so good. So what about malicious traffic and TCP/IP? I picked on AV. Let's talk about TCP/IP. So those next generation firewalls. How many next generations are we up to? This is actually my third next generation. So we had the first generation, then we had next generation, which were second generation. I can't wait for the next generation. It turns out the TCP/IP is Turing complete. And Turing complete means the halting problem applies. And if the halting problem applies, you can't look at packets and positively identify all bad traffic. You just can't. It's a halting problem. And so that next generation firewall, it's going to make things a little bit better, right? But it's just not a panacea. It's just different kinds of signatures that are going to be bypassed in new and different ways, or in old and known ways. But if that wasn't bad enough, we've got this thing called the von Neumann architecture. So most commercial systems, and there are one or two exceptions, have this key feature in their architecture where instructions and data share the same code space. And on top of that, instructions and data are represented with the same assembly level language. So given an arbitrary hex 41 in x86 architecture, it may be a capital A, or it may increment the ECX register. And every exploit takes advantage of the fact that you're expecting data and I'm feeding you instructions. In the case of return-oriented programming, the instructions I'm feeding you are jump instructions where I'm going to find arbitrary gadgets of assembly code already existing in your memory space from completely legitimate programs, and I'm going to dynamically build my payload on the fly. So even data execution prevention and address space layout randomization, they're not going to stop. They're not going to stop us. And that's just kind of where we're at today. So It's pitch black, and you're likely to be eaten by a Gru. For you old people, there was this text game called Zorik. You should look it up. So here's where we're at. We can't optimize resources because traveling salesman problem says we can't. We can't identify malicious logic because halting problem says we can't. We can't tell if our program will even stop, let alone give us a correct answer, because that's also the halting problem. And it's worse, we can't even tell if what we're reading in memory space is data or if it's an instruction. So anybody want to give up? And the bar's right over there. The bar's right over there. So how do we live with no ODate detection? The vendors will claim they can detect some 0 days using signatures and heuristics, which are really just statistical models, which is fine. The way that they're doing that is they're making assumptions. And they're making those assumptions so they can reduce the problem space so they can give us a workable solution. Again, remember that workable solution is non-optimal, so you're still going to get those false positives and false negatives. So we as consumers of those products, we need to talk to the vendors and we need to ask them, what assumptions are you making? And then we need to validate that the assumptions that they're making are sound and make sense in our operating environment. So let's walk through an example. Vendor walked into my office a couple of months ago and said, they have this next generation vector-based algorithm for behavior-based network modeling that can detect all malicious activity on the network. What does that mean? All right, next generation, meaningless marketing term, means nothing, right? It's a null. Behavior-based modeling means heuristics or statistical model, and vector-based algorithm means it's directional. Okay, so is it a valid claim? Absolutely not. They are not going to detect all malicious traffic. Can they detect some malicious traffic? Yeah, probably. Is it useful? I don't know. It depends on your operating environment, but let's see. Let's talk about an ICS SCADA system. Why are we going to talk about an ICS SCADA system? They are a physical system, so there's a computer component and there's a physical component. I don't know anybody that has anything nice to say about the state of security in ICS SCADA. It is horribly, horribly broken. ICS SCADA systems are still learning rules that the PC industry figured out in the early 1980s. They're difficult to patch if they're ever patched, and they're missing traditional defense. So when you look at ICS SCADA, these are all old Motorola controllers, in some cases old ARM controllers. They don't have data execution prevention. They don't have address space layout randomization. They don't have antivirus. They don't have IDS. They don't have any of that stuff that protects us on our Windows and Mac networks. And the protocol, while it's well understood, is still Turing complete. So basically, these ICS SCADA networks are as bad as they're going to get. So let's see if we can make it a little bit better. So what are some protocol assumptions? Well, again, we understand the protocol, but it is Turing complete, so halting problem means we're not going to detect all bad traffic. But ICS is still a fairly robust protocol. We are probably not going to use all of the ICS protocol messages in our own unique implementation. So let's just look for the ones that we're not going to use and cast those out as malicious traffic. I'm also going to make the assumption that my ICS SCADA network is my ICS SCADA network, and so I'm not going to see a whole lot of internet surfing. I shouldn't see any internet surfing. I shouldn't be seeing managed code like Java or Flash or Shockwave or all of those things that get you pwned on a daily basis. And I'm going to assume that I'm not going to have any Pokemon Go on this thing. So those are my protocol assumptions. And then these ICS SCADA have a physical component as well. And so these physical components are pumps and their valves and their pipes and their generators. I mean, these are big honking industrial systems. And those things are engineered to very precise failure tolerances. And they have physical limitations. When they're engineered to work within certain heat ranges, to work within certain pressure ranges, to work within certain speed ranges, to heat up and cool down at very, very precise rates. And so anything outside of that would be anomalous, and I should keep track of that. And then I'm going to make these operating assumptions as well. I've got these SOPs. The industrial process is going to be well understood. Again, these are large, very expensive factories, very large and expensive machinery. And so we have these standard operating procedures and actions, and anything outside of those actions should be anomalous. Now, there are times when we go into emergency response procedures, and that allows us to break out of our normal SOPs, but again, we should know that we're doing something anomalous. And not every component in my industrial complex needs to talk to every other component. If the wrong valve is trying to send a message to the wrong pump, we've got a problem. And so when you put those three operational circles together with your physical constraints and your valid protocol messages and your procedural constraints, it turns out that really this is the space that we need to operate in. That is really all we need to monitor, which is a heck of a lot less space than all of this. So that vector-based, heuristic engine, it might be okay. It might make things a little bit better. So key lessons, almost no security problem of real interest can be solved optimally by automation alone. We're going to need security analysts. We're going to need smart people that read our IDSs and IPSs and understand what's really going to go on. We need people that understand the technology and it can actually make sense of what our sensors are telling us. We can solve portions of these problems by making assumptions and understanding the risk. But when we make those assumptions, we need to understand that there is some inherent risk in making those assumptions. Different vendors are going to make different assumptions. That's actually a good thing for us because I know we've all been hearing defense in depth for a long time, but if you buy multiple vendors and they all make different assumptions, then maybe vendor B can catch an assumption from vendor A. It makes it harder to manage things, I understand that, but it does make things safer and security is not free. Understanding fundamental limits of computing are going to help you identify snake oil. Really, you can get by normally on TSP, von Neumann, and the halting problem. If you understand those three, you can sit across from a vendor and when they tell you that they detect all low days, you can go, really? Halting problem. And if they don't know what that means, tell them to bring you an engineer or computer scientist that does. And automation is great. It's going to help you reduce the noise, but it's just not going to solve the problem for you. So for the vendors, please, please, please be honest in your claims. Send me an engineer or a computer scientist. I have questions. Salespeople are great for touching base with your contacts. They're great for making new connections. They're great for maintaining connections. But if I'm going to spend a lot of money on a product, I want to talk to somebody that can tell me what's under the hood because I want to peek under it and I want to kick the tires. Your assumptions and methodologies, they're not secret sauce. If you need to have your vendor sign an NDA to tell them so that you can tell them how your product works and what assumptions you make, then by all means, I've got no problem signing an NDA, but if you're not telling me these things, I'm probably not going to buy your product. And for goodness sakes, quit selling me marketing speak. I am tired of reading an entire book full of literature and not understanding what your product actually does after it. That next generation cloud-enabled, software-defined, heuristic-based, virtualized, threat-centric, multi-layer, end-to-end, analytics, adaptive cyber defense, cloud over IP pew-pew, not worth the glossy paper it's reading on. And if you think that's overkill, please go read some of these vendor pages. You will get really excited after reading about 2 pages of text and realize that you still have no idea what that product does. So for those of us that buy these products, the vendors actually have some pretty smart solutions, right? But you have to understand what the limitations are. If they're making claims that are too good to be true, they probably are. Ask them how they're reducing the problem space and ask them what assumptions they make, and then more importantly, validate those assumptions. Make sure that the assumptions that they made make sense in your operating environment. Learn which problems can't be solved by computers and which can't be solved easily. And realistically, human operators and hunting combined with defense in depth, it's still your best solution. It's going to be your best solution in 10 years. It's going to be your best solution in 20 years. So the next time a vendor comes to you and tries to sell you Brondo, the Ode mutilator, ask them to tell you again how they solved the halting problem. So with that, are there any questions?
So I think one of the previous speakers mentioned the benefit of combined machine and human analysis. How does that play into the assumptions and help balance out what the machine's doing and improve the overall outcomes?
I absolutely agree. I was actually here for that presentation, and that's actually right here in this slide where I talk about, the good system. What he talked about was automation with a good system. So here's your good system of understanding the assumptions and understanding what the machine's going to decide for you, and then those human operators actually going through and validating what the sensor is telling you. So I absolutely couldn't agree more.
So the idea would be that the machine is acting as a kind of first level filter to prioritize things for the human.
Yeah.
Would that be a way of articulating that?
Yeah, so absolutely the machine is a first layer filter to reduce the noise and allow the human operator to spend time looking at the things that really they need to spend time looking at. The low-hanging fruit, by all means, please let the automation take care of that. And then the people can spend their time chasing down worthwhile threats.
Do humans suffer from the same problems that the machines do as far as the halting problem and such?
Humans suffer from different problems.
Humans suffer from a lot of problems.
Humans suffer from so no. I mean, the human can make the decision that if you haven't told me that this thing is halted by now, I'm not interested in it. A human can make that decision. The machine really can't. The machine can do it if a human tells it to. The problem that humans have is they suffer from boredom, and they suffer from, in some cases, a lack of education and training. And in some cases, they suffer from, most of us, a lack of sleep. And so, you know, again, it's one of those things that the assumptions of the machine and the assumptions of the human operator kind of back each other up because we suffer from different problems. Yes, sir?
Yeah, thanks for the talk. I think you're not really going far enough in your criticism of these products. So I think one big aspect that you haven't mentioned at all is that these products can introduce risks, and these risks increase over complexity. I mean, because what we're seeing with a lot of these next generation things is that these scanning engines become so complex that introduces a whole lot of vulnerabilities. There was some interesting stuff by Tavis Ormandy where he found that some antivirus was kind of emulating what a program would do, and then it would, if it cannot emulate the function, it would call the one from the system, and thereby you could get code execution through the antivirus. And also, like, you're totally right that you're hitting these theoretical borders if you're trying to get a perfect detection, but I don't think you're hitting any theoretical borders to trying to build a system that just doesn't execute foreign code. So my question would be if the whole detection approach isn't the wrong way of going, but instead we should design a system that is secure by design. And I think there's a lot of interesting research coming from the LangSec community, which doesn't nearly get the amount of attention it should get. Yeah.
So I agree with just about everything you said. So as code becomes more complex, and that's any code, it's not just antivirus, you're going to have more mistakes because people write the code. It's funny, when you look at antivirus, they actually use a lot of techniques used by exploit code. So library call hooking and root kernel interrupts and those kind of things. That was all developed originally by malware authors. It's now being used by antivirus firms. A lot of the things that Emmet does for Microsoft, and I'm a big fan of Emmet, but it uses a lot of malware techniques in order to detect malicious code. To answer the other question about the detection, the LangSec is doing some great things, but until I can tell the difference between an instruction and data, because I've got two entirely different memory setups for those, we're just chasing up the wrong tree. As soon as I mix data and instructions, and they're both represented in the same language, I'm stuck. And so now I can't tell the difference between data and instructions, and so your program expects data, I actually feed it instructions and convince the kernel to execute those instructions on my behalf. That's the real crux of the problem with the von Neumann architecture. No, we just need to change the construction and architecture of every computing platform we currently use. But no, it's not unsolvable. None of these. No. I agree with you. It's just a matter of somewhere along the line we chose to do it this way for a reason. We need to go back and re-verify that the reason that we chose to go down that path, that those assumptions are still valid. I don't think when they chose to build the von Neumann architecture, they were really thinking about the future of InfoSec. I think they were just trying to think about how do we crunch numbers as quickly as possible with as little hardware as possible. So you're right, this may be a time to go back and re-examine those assumptions. Please.
So I'm going to break up the tech talk with a sort of a soft skills people question related to this.
Yes, please.
So you mentioned about demanding to talk to an engineer. And so I'm just curious then, so again, for tips for people if you have to deal with this. So if the vendor is reluctant to do that, so what's considered a deal breaker? When do you pursue it harder? How do you deal with the pushback if they don't want to cooperate with that? So more like the soft skills, how do you deal with that?
So great question. I have found that as soon as I tell the vendor, okay, I'm done talking to you, I'm not going to consider your product, they're pretty much willing to give me whatever I want. Now, I have had some vendors go, look, I'll discuss this with you, but you need to sign an NDA. Or I'll suggest, look, if you need me to sign an NDA, I'm happy to do that. But normally vendors are pretty good, and once they realize that they're not going to get any further with you, if you're a small business, it's much harder. But if you're a larger corporation, it's amazing what they'll do when there are hundreds of thousands or millions of dollars on the line. And I've never had one significantly push back on that. Not even in government, and that's saying something. Any other questions? Okay, well with that, here's your vendor bingo card to go out there and go through the vendor space. Thank you so much, and I will see you around.